Hi, in this video we will do a quick look at our power distribution units, what their features are, do a basic configuration, then cover some more advanced features, and in the end configure a complete project from scratch. You can use timestamps to jump around the video. If you have any questions, let us know in the comments below or contact us over email. We have here two versions of our power distribution units. The smaller one has got 15 outputs, all capable of 30 amps per output. And the bigger, that one has 30 high side outputs, capable of 20 to 40 amps per output, and 8 low side outputs. Smaller unit has 8 inputs, whereas the bigger one has 16 inputs. Both have plug-and-play keypad detection and other advanced features. They both simulate common power distribution units on the market, so they can easily be integrated in your existing project. We will first connect the PDU and run the configuration software, do a quick overview of the features, then we will configure few inputs and outputs. At the end of the video, we will cover more advanced features and configure real race car. To configure any of the MME Motorsport device, you need to use our configurator that can be downloaded from our webpage. Now, let's connect to USB port and power on the unit. In this case, we will use PDU 2, which is the smaller of the two, but apart from the number of outputs and inputs, they both use the same logic. As soon as device is connected, it should be detected on the left side of the screen. Green means device is online and connected. If this turns to orange, this means either device has been turned off or USB connection has been lost. Same goes for the bottom bar. It will show you which device you're connected to. If you have multiple devices opened up at the same time, you will see it switch, depending which window you're focused on. When you connect to the device, the software loads all current settings from it. If you change any setting, you need to send those changes back to the device. You can do this by pressing F5 or by selecting Device Settings, Send Changes to Device. This step is not automatic, so remember to send the settings whenever you make a change. We will now quickly go over the PDU setup structure to get an idea of what is what. An input is a virtual switch. It can be triggered by CAN messages, physical inputs, or keypad buttons, and can then be used anywhere in the system logic. Outputs control the physical power channels of the PDU. Here you configure protection settings like trip current, trip delay, and how many automatic restart attempts are allowed after a fault. You also define the conditions that determine when the output turns on. The kill switch is a global safety input. When it becomes active, all outputs are immediately disabled, regardless of their individual conditions. The reset faults switch resets all active output faults. When triggered, it clears the error states and allows outputs to operate again. The keypads section is used to configure CAN keypads connected to the PDU. Up to 3 keypads can be used, and their buttons become inputs that can be used in the system logic. This is where you configure CAN bus speed and other parameters, which we'll discuss later in this video. PDU units have 2 different CAN buses that can operate at different speeds. Functions are reusable groups of conditions. You can combine several conditions into a function once and then use that function anywhere instead of repeating the same conditions multiple times. Variables store numeric values used by the system logic. They can read data from CAN, analog inputs, or other variables and convert it into values that can be used in conditions or output control. We will talk about these later on in the video, where we focus more at the advanced features. Every project normally starts with inputs, so let's first define 3 buttons. One button will be to turn on accessories like dash, second button will be to turn on ignition, and the third, it will be to start the engine. We open inputs by double-clicking the Setup/Inputs menu. Here you see all inputs listed. By default, all are disabled, so that's why all are gray. If I left-click on the input number, I can now start editing. Let's define first one, and let's call it ACC, as in accessory, which will turn on the dash. Let's assume we have switch wired to our physical input 1 pin. We want this button to be toggle operation. If I press it once, it will turn on, and if I press it again, it will turn off. If this was momentary, it'd be active for as long as this button was pressed. Our switches are normally connect switch that connects ground when pressed. This is called active low switch. So we enable 100K pull-up, select active low, and define thresholds. Because this will output low voltage when active, we define active when voltage is below 1 and inactive when voltage above 4. We click OK. Now, let's define our second switch. That will turn on the ignition. Because switch parameters are identical to the accessory switch, we can use Copy from Menu and just select which one to copy. Let's rename it to IGN. We have this wired to our physical input 2 pin. Click OK. Third button will be to start the engine. We copy it again and name it Start. This time, we change operation to momentary, so it will be active for as long as this button is pressed. Settings are now only visible in the software, and we need to save them in the unit, so let's press F5. Let's close inputs for now. Inputs by itself don't do anything yet, so we need to define outputs. Outputs control the physical power channels of the PDU. We click Outputs. Because this is PDU 2, we have 15 outputs available. If this was PDU 3, we would have 38. We will define 3 outputs that are controlled by our previously defined inputs. We start by clicking on the first output. We will call this ACC. We give it 5 amps max for the duration of 0.5 seconds. If current is above 5 amps for more than 0.5 seconds, fuse will trip and output will be deactivated. For output to know when to turn on, we need to define conditions under which output is active. Let's add our first condition. We will only use one condition here. As long as our accessory input is active, this output will be active. You can see summary of the condition we just added in this list. If we added another condition into this list, both would have to be met for output to run. Press OK and close this output. Second output will be to turn on the ignition. This, in real case scenario, would mean turning on coils and fuel injectors, but for this simple example, let's assume both are connected to the same output. Let's say trip current is 10 amps for the duration of 0.5 seconds. Conditions to run this at is for as long as input 2 is active. Third output will be start the engine. Let's name it Start. We give it max 15 amps for duration of 0.5 seconds. Pressing F5 now stores these settings to the unit. This is it. We just defined our first PDU. If at any time you're working on your power circuits or wiring, you can disable all outputs by pressing the Deactivate Outputs. Until you press Activate Outputs again, outputs stay deactivated, even if you power the unit off and on. A lot of cars now use CAN keypads, which is an easy-to-get, nice-looking dashboards really fast. Both units offer auto detection of most common keypads on the market. To add a keypad to your project, expand keypads and you can see that you can have up to 3 keypads connected. Let's add first keypad. We need to select which channel we have the keypad connected to. If you know the addresses, you can enter them here, but in our case, we will just use auto detection. We select channel 1, 1000K speed, and click Start Auto Detection. Software found our connected keypad. Now we click Use this keypad and close. As soon as we send changes to the unit, we can test the keypad. If you see green OK on the top, this means keypad is working. To the right, you will see buttons boxes lighting up if you press any of the buttons. If we now go back to the inputs and edit button 1, you can see that we can now change the source to keypad 1, button 1. Now, input is no longer a physical switch, but a keypad button. Let's assign other inputs too. Ignition switch will be keypad 1, button 2, and start switch will be keypad 1, button 3. We need to press F5, and now we have a keypad-operated outputs. Let's now go back to the keypad and set how we want for keypad buttons to light up when we press them. Depending on which keypad it is, you will have different settings available. This one is Blink Marine PKP, which is capable of setting different color for each button. Indicator can be steady or blinking. You can define backlight color and backlight brightness. Indicator B1 means indicator for button 1. B2 means indicator for button 2, and so on. For each button, you can set condition that turns that indicator on and its color. You can edit that condition by left-clicking the condition. For our simple example, we will choose condition to turn the LED on whenever input 1 is active. We also want this button to be blue when active. For button 2, we want it to light up when input 2 is active. Color for that button is green. Lastly, we set button 3. This is our starter button, and let it be red when active. F5 will make this permanent. Note that this is only a very basic setup. You can define more complex conditions, and we will cover that later on in the video. We will now set up a real race car. What every car needs is a master switch. It is normally connected directly to the battery positive and can handle huge currents. We have two common setups. One setup uses a standard FIA master switch, which can be seen in this diagram. Usually these are also cable triggered, so the car can be turned off from outside the car as well. There is a separate wire that will let our PDU know that we are turning the engine off. We will wire this signal to input 1 and use it as a global kill switch. Another option is to use an external relay like TE with one internal and one external kill switch. It is important that both are toggle operated and not momentary. An example diagram is shown here. For this case, we will use the following physical inputs. Kill switch, which we already described, will be wired to input 1. ECU fuel pump signal is also active low and will be on input 2. This is the signal that our ECU sends when it needs fuel. Normally, the ECU does this when the car is turned on, if prime pulse is enabled, or when it detects the engine turning. It will keep this signal active for as long as the engine is running. For safety reasons, we do not want any coil or injector activity in the car if this signal is not present. ECU fan signal is also active low and wired to input 3. The ECU sends this when engine temperature is high enough that it needs cooling. The fan could also be turned on by the PDU itself by reading engine temperature, but for this case, we will use a physical wire from the ECU. The last physical wire is wiper park switch. This is a 12-volt input that indicates the wiper is at 0 position. Our logic needs to stop the wiper when it parks. We will use a Motec keypad from Fiesta R5. This is a can-open 15-button keypad with 3 LEDs at each button. For this example, we will use these keys. Ignition, which is on button 15. This will turn on our coils and fuel injectors. Fuel pump, which is on button 13. Engine fan on button 14. This button will override our engine fan, and if active, will turn on our fan output regardless of the ECU signal above. Start on button 3. Lights on button 2. This will turn front and rear lights on. 2 blinker buttons for left and right, which are on buttons 4 and 5. 4 blinkers on button 9 that turns left and right blinkers on. And finally, washer on button 7, which will turn on the windscreen washer pump. As far as outputs go, we have ECU, dash, and other sensors on output 1, coils on output 2, fuel injectors on output 3, fuel pump on output 4, engine fan on output 5, starter on output 6, front and rear lights on output 7, rear brake light on output 8, left and right blinkers on outputs 9 and 10, slow wipers on output 11, fast wipers on output 12, and washer on output 13. Output 14 and 15 we will leave disabled for now for future use. Let us open inputs and start adding them one by one. Input 1 is our kill switch, which is on physical input 1. This is a momentary switch that is inactive if ground is connected. As soon as ground is lost, which means we're shutting the car down, we need to turn it on. We do this by enabling pull-up resistor, so we have positive when nothing is connected to this input, and set it to active high. Activate it above 4 volts and deactivate it below 1. In normal car operation, we will have ground here, so input will be low. As soon as master switch is deactivated, there will no longer be ground connected to this, and we will get positive value. This will then turn off all outputs so car can shut down properly. Input 2 will be our ECU fuel pump signal on physical input 2. It is active low, so we enable a pull-up and set thresholds accordingly. Input 3 is ECU fan signal on physical input 3. We can copy it from previous one and rename it. Input 4 is wiper park switch on physical input 4. This one is a 12 volt signal, which PDU will read as 5 volts when active. We set this to active high and set the threshold to be active when higher than 4 volts and inactive when lower than 1 volt. We will now add keypad buttons. We have already used auto detection and we have our keypad connected as keypad 1. We will start with input 10 to leave some space in case we add any more physical inputs to our PDU in the future. This is just to keep the physical and CAN inputs separated. Ignition on keypad 1, button 15. Operation, toggle. Input 11 is fuel pump, and so on. We will speed up this video while we add the remaining inputs. We are done adding inputs. Apart from start and washer buttons, which are momentary, all other buttons are toggle. We can now test the buttons to see if they work. You will see that when a button is activated, it turns green. We do not have any indicators turned on the keypad yet, so let us define those now. This keypad has 3 separate LEDs on top of each button. B1/L1 is button 1, LED 1. B1/L2 is button 1, LED 2, and so on. To go to our first button, ignition, we need to go to button 15, which is on the 5th page. We want all 3 LEDs to be on whenever this ignition button is pressed. So we click Condition next to the indicator and set it to be active whenever ignition input is active. We do the same for the other 2 LEDs. F5, and let us test if these buttons work. We now do the same for fuel pump, engine fan, and lights. Let us test those. Blinkers, wipers, and washer we will leave for now, since they will be operated differently. Time to configure the outputs. If you have the PDU connected to a live car, it is recommended to first deactivate the outputs while we work on them. You will still be able to see if they are virtually working, but they will not physically output anything. Output 1 is dash and ECU. In this example, it will also include something like oxygen sensors, but if possible, non-critical stuff should be on a different output. If this trips, the ECU will trip too. We give it 10 amps max for the duration of 0.5 seconds. And we want this to turn on with the PDU, so under conditions, we will add always on condition. Next, we will add fuel pump to output 4. We give it 25 amps for the duration of 0.5 seconds, and the condition to run is ECU fuel pump input is active, and fuel pump keypad button is pressed. Both conditions need to be met for the fuel pump to turn on. This also means that before we start the car, this button needs to be pressed. It will also allow us to build oil pressure when cranking with the fuel pump turned off. The reason we added fuel pump first is so that we can now use this output as a condition for coils and fuel injectors. We do not want fuel injectors or coils running if fuel pump is not active. Now let us add coils. This will be on output 2, and we give it 10 amps max for the duration of 0.5 seconds. We want this output to be active only when ignition button is pressed. And we add another condition. This time, we will use if output active. We only run this when fuel pump is active. If fuel pump turns off for any reason, coils will be deactivated too. Some engines prefer burning out all fuel from the cylinders before shutting down, so they allow fuel pump to turn off while coils are still running. In this case, we would just remove the fuel pump condition we just added. We will leave it on for our case. Output 3 is fuel injectors. Five amps max for the duration of 0.5 seconds, plus only active when fuel pump output is active. We do not want fuel injectors to run if fuel pump is not turned on. We do allow fuel injectors and fuel pump to run with ignition off, so any fuel priming pulse can normally occur. Engine fan is on output 5. We set 30 amps max for the duration of 1 second. Condition to run will be either ECU fan signal is active or our keypad fan override button is pressed. We put this condition in the second box. These motors can have big inrush currents, so we will use soft start feature here. There is no need for this fan to turn on instantly, so we will set it to start gradually in 2 seconds. We enable PWM frequency, set it to 100 Hz, set final duty cycle to 100%, and enable soft start with the duration of 2000 milliseconds. We will leave it like this for now, but later on we will set duty cycle depending on the engine temperature from the ECU. Starter on output 6 will have max 25 amps for the duration of 0.5 seconds. Activate it when start keypad is pressed. We will leave it like this for now, and later on we will add another condition to only run this if the engine is not already running. We need RPM reading from the ECU for this, and we will return to this after we do that. Output 7 is front and rear lights. Note that halogen light bulbs, like H7 or H4, draw huge current on cold start. They are basically a short circuit for a few hundred milliseconds. If you run up to 2 bulbs at the same time, this is fine. But for more, you need to use soft start function. Recommended soft start is around 1 second at 100 Hz and 100% duty cycle. In our case, we will just set it to 15 amps for the duration of 0.5 seconds. Condition to run is input from the keypad. Rear brake light on output 8 should turn on when brake is pressed. Now this can be another physical switch wired from the pedal, or brake pressure switch, or something else. For our case, we will assume we have Bosch ABS installed and we read the brake pressure from the CAN bus. We will return to this later on, and for now, we will only set trip current 5 amps for the duration of 0.5 seconds. Because no conditions are set, this means that output will be permanently off for now. Time to set the blinkers on output 9. Five amps max, and we will set trip duration to 0.4 seconds. We will use flash function for this. We want it to flash in 0.5 second intervals. Flash on for 0.5 and flash off for 0.5. The reason we chose 0.4 seconds is because when flash function is enabled, trip duration must be shorter than the flash on interval. Condition to run will either be left blinker keypad or all 4 blinkers from the keypad. We do the same for right blinkers on output 10. We will copy settings from the left blinker, rename it, and change first condition. To edit existing condition, we just double-click it. We have 2 speed wipers installed. One output powers slow speed and the other is high speed. We want to use one keypad button for this. If we press wiper button once, we want slow speed, and if we press it twice, it will be high speed. If we press it the third time, wipers should turn off. Before we can use this, we need to let the PDU know that we want to keep track of how many times the button has been pressed. We do this by opening the inputs. Click our wipers input and enable checkbox to count the presses. We enter 2 because we want 2 presses maximum. After the 2 presses, this will reset to 0. When we enabled this counting, you will notice that you now see how many times the button has been pressed next to the input name. If we press it a few times, it should increase, then go back to 0, and so on. Now back to our wipers output. We have it wired to output 11. Max 10 amps for the duration of 0.5 seconds. Here we use condition input active and number of presses, select our wiper keypad button, and set condition to run only if this is exactly 1. It will be 1 the first time we press it. High-speed wipers on output 12 is max 15 amps for 0.5 seconds. We use same condition as before, but this time we want this output to activate when number of presses is exactly 2. When wipers stop, we do not want them to stop immediately, but to go into park position. That is why we need to add another condition. After deactivation, we want wipers to keep running until park switch inside the wiper is activated. We defined our park switch in inputs, so we just add it in the bottom box, where we have keep running until conditions. If you only had 1 speed, so only 1 output for wipers, you would use this condition there. In our case, we never turn off wipers in the slowest speed, so we use park switch only in our high-speed output. Washer, on output 13, is a simple motor that will be spraying water for as long as the keypad button is pressed. Max 5 amps for 0.5 seconds. We can keep this simple or we can add a bit of automation. Let us say for now that we want this to run for 2 seconds after we press it, so we do not need to hold it. We add start condition to be active when washer keypad is pressed, and we set it to keep running until duration of this output is higher than 2 seconds. As soon as this condition is met, it will turn off. To make it even more automated, we can add 2-second spray, activate the fastest wipers, and then park them. To set this up, we open our fastest wipers output and add another starting condition. Turn this on if washer output has been active for more than 1.9 seconds. This duration after output activated is only valid for running outputs, so it is important that duration is below 2 seconds to allow this condition to be met. And just like this, we have fully automated windshield cleaning configured. We now go back to the keypad where we left off and still need to define LEDs for washers, wipers, and blinkers. Washer is on button 7, so we open that and define that all 3 LEDs are active when output washer is active. For blinkers, we will do the same. But in this case, we use output pin active condition. Output active represents the logical or virtual state of the output. So for blinkers, this stays active the entire time the blinker function is enabled. However, the actual output is flashing, turning on and off physically. What we want instead is to follow the real electrical signal on the output. That's why we use output pin active. This reflects the actual physical state of the output pin, so it turns on and off together with the blinking signal. This way, the keypad indicator will blink in sync with the output, giving us the correct visual behavior. We do the same for the right blinker as well. For 4 blinker LEDs, we need this to blink whenever 4 blink input is active and either of the blinkers is working. Because we can only define one condition here, we can't use multiple scenarios, so we will need to add a function. We open functions and define a function that will turn on the 4 blinker LEDs. Conditions for the LED are if 4 blinker input is active, and output pin for left blinkers is active, or 4 blinker input is active and output pin for right blinker is active. Wiper LEDs too need to be active when either of the wiper outputs is active. So let's add that too. We add new function. And add condition if low speed wiper output is active or high speed wiper output is active. We then use these functions at the keypad. We now have a pretty decent configuration that can run many cars. The only thing left to do is our kill switch that we defined previously in the video. We open Kill Switch Input option, activate it, and select our input 1. Whenever this button is active, all outputs are turned off, regardless of their state. Now we can test the outputs and see if everything is working. It is best to do this with outputs turned off first to verify the logic works, and then test the trip currents and other settings with outputs turned on. When testing, if you right-click on the output, you can force the output to turn on, turn off, or set it back to use conditions to run. This is very useful when testing trip currents and output logic, as it's easy to simulate different scenarios by forcing different states. This works for inputs and functions too. Going back to our brake light switch, we mentioned that we will be using Bosch ABS unit and read pressure from the CAN bus. For this, we need to create a variable. We could add it manually if we knew CAN bus dataset information, but in our case, we'll just import this variable from CAN-DBC file. We click Import Variables from File, select File, select our DBC file, and click Open. It'll list all signals and show current live value of this signal on the CAN bus. We look for our front brake pressure signal, which is called P_FA. We check that one and click Next. On this screen, we tell it where we want this variable to be stored to. We leave it at variable 1 and give it a name. Click Next. We will add another 2 ECU signals while we're at it. In our example, we're using Syvex S7, so let's add engine RPM and engine temperature to our variables. Click Next and assign them to variable 2 and 3 and rename them. Click Next, and this time we will send the settings. Variables should light green, and we should see the values changing. If you see variable go to orange, this means that CAN signal has been lost. You can set the default value in case variable is defaulted, how long it needs to be missing to be defaulted, or disable this check altogether. We will cover this later on, where we go into more details. Now we can use these variables in our conditions or map them in another variable. Let's update our outputs now. For rear brake light, we want it to light up whenever the front brake pressure is more than 10 bars. We add variable condition and set it accordingly. Now, output will turn on when we have more than 10 bars brake pressure. For starter, we will add that it will only turn off if engine is not running. We open starter output and add another condition. Activate it only when RPM is between 0 and 1,200. If over 1,200, starter will be disabled. Similarly, we can use our engine temperature variable now to turn the fan on and off. Let's open our fan output and remove the current physical wire condition. Add variable condition to start the fan if engine temperature is over 85 degrees Celsius. To add some hysteresis to it, we want to turn it off when it reaches 80 degrees or lower. We add keep running until engine temp is between -25 and 80. Let's now assume we want to control the fan duty cycle based on engine temperature. In practice, this is not ideal because running the fan at partial duty cycle for long periods can cause the drivers to heat up. We are using this only as an example to demonstrate how to create a variable that takes one source and maps it to a different output value. We create new variable, name it, then select source of this variable to be our engine temperature. We select number of points to 3, and we want fan to be off below 60 degrees and mapped from 0 to 100 between 60 and 85 degrees. Everything above 85 degrees will clamp to 100%. We will now stop the car and do temperature simulation to see how duty cycle of the fan changes. We open outputs and fan output again and set that our target duty cycle is not 100% anymore, but rather defined by our new variable. Whatever variable we use here needs to be 0 to 100%. Everything below and above that will be ignored. We also change start condition to be above 65, so our duty cycle calculation can kick in and change keep running until condition to below 60 degrees. There you go. We finished setting up our real race car example. There's one last feature worth mentioning. When your PDU is running for a while, you can check the long-term health of your outputs. If you go to logs/stats, you'll be able to see how they have performed and if there are some that need attention. Here you can see the total on time, how many times the output has been turned on, what the max current was, what its average current is, average load based on trip current, how many times it has started tripping and the total duration of it, and lastly, how many times it has tripped. You will see different state colors. Green means the output is healthy, orange means that you need to pay attention, and red means there were some issues with it in the past. Either it has been overloaded, close to overload, had too many trips, and so on. Reset stats will reset all values to 0 so you can start fresh. On the right side, you can check certain events that have occurred. You will see the total number of overcurrent, overvoltage, undervoltage, CAN bus errors, and similar issues that affect the PDU. That's it for this video. If you would like to know more about the product, visit our webpage, www.mme-motorsport.com. Thank you.